All right, today we're going to crack open one of the most powerful problem-solving strategies ever. Seriously, it's a technique that takes these huge, impossible-looking challenges and just breaks them down into simple, manageable steps. We're talking about something called divide and conquer.
So let's just start with a really big question, one that I'm sure you've faced. You're staring down a massive, super complex, totally overwhelming project. Where do you even begin, right? How do you tackle something that just feels impossible? Well, the answer is actually something you probably already know deep down. It's super intuitive. You don't try to swallow it whole. No way. You chip away at it. You find one little piece you can solve, and then you find another, and then another. You literally divide the impossible into a bunch of smaller, possible tasks.
Now, this simple idea, this intuition, in the world of computer science and algorithm design, it actually has a name. And believe me, it is an absolute cornerstone of modern computing. It's called divide and conquer, and it's this beautifully simple concept that has some really profound implications.
Okay, so there's a formal definition for it, but the main idea is exactly what we've been talking about. You split a big problem into smaller, almost identical versions of itself. Then you solve those easier, bite-sized versions. And finally, you find a clever way to stitch all those little solutions back together to solve the big original problem. Simple as that.
So how does this actually work in practice? I mean, what are the steps? Well, it follows this surprisingly consistent and predictable, you could almost call it a three-step dance. So let's break down the choreography. Step 1, divide. You take your main problem and you just split it into smaller subproblems. Step 2, conquer. And this is where the real magic happens, usually with something called recursion. You just keep breaking those subproblems down and down until they're so tiny they're, well, trivial to solve. And finally, step 3, combine. You take all those little solutions from the subproblems you conquered and you merge them all together to get your final answer.
And here you can see that flow perfectly. Imagine you have a big problem, let's call it size n. That divide step splits it into smaller pieces. The conquer step tackles each of those on its own. And then that combine step brings the results back together. That's the core loop, the mantra, really. Divide, conquer, combine. Now, when you actually write code for this, it often looks like what's called a recursive function. The best way to think about it is like one of those Russian nesting dolls, you know? To open the big one, you have to open the next smaller one inside it, and then the one inside that, and so on. A recursive function is kind of the same. It solves a problem by calling itself on a smaller version of the problem, over and over until it gets to a version that's so tiny it's super easy to solve directly. This whole idea of self-reference, that's the engine that drives the conquer step.
Okay. Theory is great and all, but let's see this thing in action, right? Let's take our first real-world example, binary search. And this is an algorithm that a lot of us actually use intuitively, maybe without even realizing it. Like, think about looking for a name in an old-school phone book or finding a word in a dictionary. The logic behind this is it's pure elegance. Here's what you do. You take a sorted list. That's key. It has to be sorted. And you open it right to the middle. Is the thing you're looking for right there? Probably not. So is it before or after the middle? Based on that one question, you get to instantly throw away half the list. Boom, gone. That's your divide step. And then you just do the same thing all over again on the half that's left. It is so efficient. So just how efficient are we talking? Well, in computer science, we have this notation to talk about an algorithm's speed when the data gets really, really big. And for this, the complexity is called log n. Now, don't get hung up on the symbols or the math. Just focus on what log n means. It means that even if you double the size of the list you're searching, it only takes one extra step to find what you're looking for. Think about that. To search a list of 1 million items, it takes at most like 20 steps. That is the incredible power of cutting the problem in half every single time. Okay, so searching is one thing, but what about something even bigger? What if you have to sort an entire, massive, jumbled-up list from scratch? For that, let's look at a more complex, more powerful example of divide and conquer, a truly legendary algorithm called merge sort. The strategy here is it's beautiful. Merge sort takes a list and just divides it in half. And then it divides those halves in half. Again, and again, and again, until it's left with nothing but a whole bunch of tiny lists with only one element each. Now, why would it do that? Well, think about it. A list with only one item in it is, by definition, already sorted. That's the conquer step. It's solved by default.
The real work, the magic, happens in the combine step, where it cleverly merges all those tiny sorted lists back together into one big sorted list. And it's interesting to compare merge sort to another famous sorting algorithm called quicksort. Quicksort is really clever, but it can be a little unpredictable. It divides the list based on the values of the items inside. Merge sort, it's much simpler. It doesn't even look at the values when it's dividing. It just blindly chops the list in half based on its position, right down the middle every time. And that simple, predictable way of dividing is the secret to why it's so rock solid and reliable. All right, so we've seen it works for searching, we've seen it works for sorting, but what's the secret sauce here? What's going on under the hood mathematically that makes this whole approach so incredibly fast and powerful?
Well, it all comes down to something called a recurrence relation. And that sounds complicated, but it's basically just a formula that describes how fast the algorithm is in terms of itself. It's like it's asking a question. Hey, how long does it take to solve a problem of size n? And the answer is, well, it's the time it takes to solve all the smaller subproblems, plus the time it takes to do the dividing and the combining. That's it.
Now, solving those equations can get pretty hairy, so computer scientists came up with this really powerful shortcut, and it's called the master theorem. You can think of it like a cheat sheet. We're not going to get into the actual formula, but it lets you just look at how an algorithm divides a problem and how it combines the solutions. And based on just those two things, you can immediately figure out where the bottleneck is. Is it the splitting and combining? Is it the conquering? Or is everything perfectly balanced? In that balanced state, that's usually the sweet spot for efficiency.
And when you apply this kind of analysis to merge sort, you get a runtime of n log n. Again, don't stress about the symbols. Just know that this n log n result is pretty much the gold standard for sorting algorithms. What it means is that even as your list grows to millions or even billions of items, the time it takes to sort it grows in this very controlled, predictable, and super efficient way. It just scales beautifully. It never just slows to a crawl.
So let's just sum it all up. The advantages are crystal clear. First, these algorithms are incredibly fast, especially when you're dealing with huge data sets. Second, they're precise. They often solve problems in the best possible way. And finally, they are just so stable and reliable. They don't have these disastrous worst-case scenarios that can totally torpedo other kinds of methods.
And that really brings us to the main takeaway. Look, this isn't just some abstract computer science trick. It's a fundamental strategy for thinking. Whether it's a huge project you've got at work, or maybe learning a brand new skill, or even just tackling a personal goal, the exact same logic applies. Break it down, solve the little pieces, and build your way up to the solution. So that leaves one question. What's the next big, impossible problem that you're going to divide and conquer?